Hello everyone. My name is Mohit Pathak. Today, me and my team, Sanyog, Vasishtha, Jatin, Kumar, Raghav, Chaudhary, under the supervision of Sidharth Bansal, present our project on design and simulation of a magnetic refrigerator.
So, magnetic refrigeration. Magnetic refrigeration represents a revolutionary solid-state cooling technology founded on magnetocaloric effect, offering a sustainable alternative to conventional vapor compressive system. Key advantage: zero greenhouse gas emission, compact and environmental, higher energy efficient, and operational performance. Project objectives. First one, CAD design. Develop a compressive magnetic refrigeration model using industrial standard CAD tools like SolidWorks. Multi-physics simulation. Simulate magnetic and thermal behavior using ANSYS. Perform analysis. Evaluate critical parameters including temperature, cooling power, span, and coefficient of performance. Last, sustainable cooling. Explore eco-friendly cooling solutions using magnetocaloric material. Now, what is magnetic caloric effect? Physics behind physical mechanism behind it. When an external magnetic field is applied to a magnetic caloric material, magnetic dipoles aligns, resulting in decreased entropy and increased temperature. Heating phase. Upon field removal, dipoles return to disordered state, absorbing heat from the surrounding and producing a cool effect. There are two critical parameters. First one, adiabatic temperature change. Second one, magnetic entropy change.
Now let's talk about the active magnetic refrigerator cycle or AMR cycle. The AMR cycle converts small adiabatic temperature changes into particle temperature differences by using regenerative heat exchanger. It works in a way similar to Brayton refrigeration cycle. The cycle consists of four main processes: adiabatic magnetization, isolate heat rejection, adiabatic demagnetization, and isofilled heat absorption. And the first one is adiabatic magnetization. When a magnetic field is applied to the magnetocaloric material, the magnetic moments align, causing the material to heat up as its entropy decreases. And after this, isofilled heat rejection. In this stage, the heat transfer fluid absorbs the heat from the magnetized material and transfer it to the hot reservoir. After that, adiabatic demagnetization. When the magnetic field is removed, the material's entropy increases and it cools down. And after this, isofilled heat absorption. Finally, the fluid flows back through the refrigerator and absorbs heat from the cold reservoir, producing the cooling effect. So overall, the cycle allows continuous heat transfer between hot and cold ends using the magnetocaloric effect, which is the key working principle of magnetic refrigeration. Now let's discuss the system architecture and its main components of the magnetic refrigeration setup. The system mainly consists of four key points: magnetocaloric material, magnetic field generation, heat exchangers, heat transfer fluid. The first one is magnetocaloric material. This is the active working substance that show a strong magnetocaloric effect near its operating temperature. It's responsible for heating up and cooling down when the magnetic field is applied or removed. And after this, magnetic field generation. To create the magnetic field, we use a Helbach array configuration. This setup provides a strong and uniform magnetic field while minimizing stray fields, improving system efficiency. And then heat exchangers. These are placed on the hot and cold side to transfer heat effectively. They ensure efficient thermal management between the material and the working fluid. And after this, and the final one, heat transfer fluid. This liquid medium continuously moves between the hot and cold reservoir, shutting heat and maintaining the cycle operation. Finally, the system as a whole requires precise integration of thermal, magnetic, and mechanical subsystem to achieve the best possible performance. Now let's talk about the selection of the magnetocaloric material, which is the core of the magnetic refrigeration system. The performance of the AMR system highly depends on the properties of the magnetocaloric materials or MCM. An ideal MCM should show a large magnetocaloric effect, meaning it should exhibit a significant change in temperature when exposed to or removed from a magnetic field. Among various materials studies, galvanodium is one of the most common used because it shows a strong magnetocaloric effect near room temperature around 293 Kelvin, and it shows good thermal conductivity, and it is chemically stable and easily available for research purpose. And for different temperature ranges, other material like silicon and phosphorus compounds or manganese systems are also used because they offer highly efficiency or low cost. So the final material selection depends on desired temperature range, magnetic field strength, cost, and availability.
Moving forward to CAD design and 3D modeling, we have used SolidWorks software for designing all the components and assembly of our active magnetic refrigeration system. The components include active magnetic refrigerator, evaporator, hot side heat exchanger, and gear pump. Further simulation is done on ANSYS, where we have done geometry and meshing. We have established boundary conditions for our simulation. We have did transient analysis, including computational fluid dynamics, flow simulation, heat and temperature simulation, and magnetic simulation also, magnetic field simulation.
So for our conclusion, we have key findings like magnetic refrigeration successfully manipulate entropy without gas compression. Simulation confirm efficient entropy exchange between magnetic and lattice system. Design feasibility validated through CAD and ANSYS analysis. AMR cycle enables effective room temperature cooling. Or for future work, optimize regenerator geometry, explore cost-effective magnetocaloric materials, and develop experimental prototype for validation testing.